Hello, and welcome to this presentation of automated CPE labeling of CVE summaries with machine learning. My name is Emil Wåreus, and I'm the author of this paper together with my supervisor Martin Hell. I'm affiliated with Debrict, a startup in Malmö that is building a tool for managing open source vulnerabilities. But I'm also affiliated, as well as Martin, with the Department of Electrical and Information Technology at Lund University in Sweden. Today we'll be looking at this research, and I'll start off by introducing and motivating why this research is important. We'll look at some particular challenges in analysis of disclosed vulnerabilities in open source. We'll also go into some related research and look at their past performance. And then we'll go into our solution and our system where we extract CPEs from the CVE summaries with machine learning. We'll compare these our results to the related research, look at some benchmark, and then we'll draw some final conclusions about the research and the system and suggest a couple of improvements that could be made in the future. In 2019, Synopsys conducted a research project where they found that 96% of companies that develop software use open source. And for those companies that use open source, about 60% of their code stack can be regarded as open source. Open source is an enabler of developing faster and better products and more secure products as well. But it exposes a new type of threat where the developers that develop the proprietary software might not know as much as about the code that is open source as their own code. For this, we need to develop a new type of tool that monitors open source software and open source software vulnerabilities and enables developers and security professionals to work with those in an efficient manner. Such tools usually perform software composition analysis to find out what open source you're actually using and map that open source into existing vulnerabilities that are found in places such as the National Vulnerability Database, NVD, and security advisories. They are usually presented with some type of list of vulnerabilities, a more thorough information of the vulnerability with the severity scores and such information. They usually prioritize tasks to enable other developers or security professionals to solve and remediate these vulnerabilities that they have imported into their system. And these are typically solved by bumping the version or patching the open source software. To understand the problem we are trying to solve, let's look into some terminology of the industry. We are looking at CVEs, which are vulnerabilities that have been disclosed by a CVE numbering authority, where a CVE is a common vulnerability and exposure. Each CVE has assigned a CVE identifier, which is unique. It has some metadata to it, but the important part for us is the summary, which is a short description by humans that describes the vulnerability. Those usually contains some information about the software that is vulnerable, some information about the vulnerability itself, what type of vulnerability it is, and a description of the version ranges of that software that is vulnerable. Each CVE should be linked to one or more CPEs, which is a common platform enumeration. The common platform enumeration is a unique identifier for a specific software. These softwares can be both proprietary and open source, but we are mostly interested in open source for this project. So here we can see that the CPE has a vendor and a product that uniquely identifies the software Xrog and Xrog server. It also has a specific version range, which is 1.16.3. And as you can see in the summary, this can actually be found here as well, and easily read by humans, and the software can be found through the summary. Other CPEs that actually are linked to the CVE may not be found in the summary because they are vulnerable out of the context of the vulnerability or the context of other CPEs. In this case, it might be that the Solaris system is using XROG server. But there are challenges to this because it is the CNAs that analyze these CVs when they find them, and a CV is only disclosed with a summary, a unique CV ID, and at least one reference. So there are no CPEs linked to the CVs initially. In 2015 and earlier, there was CPEs linked to all CVs within 0 days in the median case. But from 2018 and ahead, this delay has increased a lot. So CVs are disclosed and publicly available without a machine-readable link to a CPE that can be linked with software composition analysis. So this poses a challenge where the vulnerabilities are publicly known and disclosed, but the tools cannot find them. So what we want to do is we want to parse the summary and see what softwares we find in the summary and what version ranges we find in the summary, to see if we can link those to the results from the software composition analysis and find those newer vulnerabilities. We have some related research on this area that has been performed by other institutions. Here we have Glance et al. From 2015, where the focus was on adding and enriching CPEs and CVEs with additional information. And they have a similar approach that we have with something called entity detection, and they achieved an F-measure score of 70%, which is respectable. We also have ELBAS from 2019, which focus on human analysis support, where they want to generate a prioritized list of possible CPEs and CPE words that the analysts, the CNAs then can use as a hint towards what CPE they should assign. This was a TF-IDF-based training system which works much like a lexicon feature that we are going to describe later. This is not as comparable to our results in a way, but if we were to make a fair comparison with their top predictions, they would have a precision of 60%. If we're looking at our approach, we have extracted a dataset from NVD of about 130,000 vulnerabilities. And from that we extracted a training set which is much smaller but of high quality, where we could accurately map each CPE into the summary. And from that training set we created a validation and testing set as well for measuring performance. And we trained the machine learning model to reconstruct those CPEs. So in the future we could find new CPEs on summaries that we never seen before. To perform this task, we use named entity recognition, which is a task within machine learning and natural language processing. For named entity recognition, we produce a prediction for each part of the sequence. So for each word, we produce a unique prediction, and we are trying to label up each word, for our case, as a product or vendor or version. We have an example here with the XROG and server being predicted with product, and the version here is being predicted with the version and excluding. We also have B and I annotation, where the B stands for begin and I stands for in. This enables us to produce multi-word predictions where one product or vendor or version can consist of multiple words in the sequence. To perform this classification, we are using a deep neural network. It is a BLSTM layer based neural network, together with a conditional random field layer that takes conditional probabilities of the output predictions into account when performing the final predictions. The input to this neural network are 4 different features that we have engineered. We have a base model that takes word embeddings, which is a conversion from string words into a vectorized numerical representation of these words that bears semantic meaning. Those word embeddings are pre-trained and for an English vocabulary and specific to general English purposes. We also create a custom character level embedding where each character in the alphabet is assigned a numerical vector representation. We create new word level embeddings from those character level embeddings with a CNN layer together with a max pooling layer. As two optional features, we have the case features and lexicon features. The case features regard specific word properties such as the casing, if it's upper initial or everything is upper, if it's all lower, or the numerical saturation. I will go more into depth into all these features later. We have also tried out a security lexicon based on past CPEs to see if that could bring additional signal into our model. If we look closer at the word and character level embeddings, we first input the raw document into a sequence where we split each word into its own entity. And we only use lowercase here and try to remove as many stop words as possible, such as the and un. For the word level, we then use a word lookup table where each word is mapped to the numerical representation, the embedding. And then after that we gain an output tensor which has the shape equal to the batch size, the sequence length, and the word embedding size. We use glove word pre-trained embeddings which come in the size of 50, 100, 200 or 300 and we chose those on hyperparameter optimization. For the character level embeddings, we split each character into a nested list where we have split the words as well. We keep the casing level and use a special embedding for upper and lower cases. We use a similar strategy here where we have a character lookup table where we get a character level embedding, a numerical representation. We use dropout to regularize this type of embedding, and then we get an output tensor of batch size, sequence length, and then we have the word length as well and the character embedding size. So this is 4-dimensional in comparison to 3-dimensional as the word embedding. To reduce the dimension into something that we can concatenate later, we use a convolutional layer together with a max layer where we get an output which is batch size, sequence length, and number of CNN filters that we end up using, which is 30 in our case. For the case level features, we have these 7 cases where a specific word can be either numerical, mostly numerical, or contains numerics. Or it can be all lower, all upper, initial upper, or it defaults to our default case. Similarly, we split the summary into the words, but we keep the casing. We'll have a lookup table where we get the case type, and for the case type we look up a custom built case embedding that is a numerical representation of that particular case in a vectorized form. And then we get an output of batch size, sequence, and case embedding size. And these are custom trainable embeddings that are tuned during model training. For the lexicon features, we extracted a number of product vendors and product and vendors that same word can be in both to build a lexicon. We tried to include the most common ones, so the range varied from the 80% most common entries to 90%, but we ended up going with 80. So it's very similar to the case lookup sequence, where we have a summary, we do a lexicon matching sequence to try to find which words belong to a lexicon entry. We get the list that is the same length as the word sequence, and we get either none, which is it doesn't belong anywhere, or we get a vendor, product, or product and vendor case. We have a lexicon lookup table, which creates a numerical vectorized representation of each lexicon type. And then we get the final tensor with the lexicon embedding size in the end. In the end, we concatenate all these 4 features into one single tensor, which is then fed into the neural network. And for the neural network, which is a quite standard BLSTM neural network, we do hyperparameter optimization, and we trained 16 models in parallel. In total, each training iteration sequence, we trained about 140 to 200 models to find the optimal tuning of the hyperparameters. The interesting thing here is that the results ended up being that we should not use the lexicon and we should use the casing. For our final result, we extract the CPEs from the sequence predictions and try to reconstruct the CPEs from the summary as accurately as possible. This enables us to find new CPEs that are not mapped in previous CPE databases. Looking at our results, we get an F1 measure in the only case model, where we have an 86% F1 with a quite high precision and a quite high recall. So we can see that the validation set and the test set are both giving us the same results with the highest F1 score in the only case model. If we compare this to Glantz et al., we can see that we have significantly improved the results here, and we believe that these are comparable since they also measure on entity detection level, which is at the same level as we are measuring. If we look into the error analysis of our results, we can see that on your right, we have a graph of the F1 score and the label count, which is the amount of entries for that particular label in the training dataset for each label type. And we can see that there's a strong correlation between having very few entries in the training set and having a lower F1 measure. So this speaks for the term of acquiring more data. And on your right, you can see the error contribution for each type of individual error. And if we look at the 4 largest entries here, we can see that the I is always contributing more error than the B. So this also speaks for that it's hard for multi-word classification and that we need to acquire more data with multi-word labels. And as we discussed earlier, the lexicon feature did not increase our performance, which might seem peculiar at first, but looking at the distribution of the CPEs and how often each CPE is mentioned, it's actually 60% of all CPEs are only mentioned once, which means that when they first were mentioned, a lexicon would not provide additional signal to perform that prediction. And if this statement holds true in the future, we see that there needs that we contextually extract each CPE from the summary rather than relying on a lexicon structure. So in the end, we instead of having a 35-day time lag, we find 86% of the products accurately. We find 84% of all versions correctly, and we could actually replace a human level analysis on 67% of all the cases. And if we don't regard versions, which could be extracted through simple regex if we had the right vendor and product, we found that we could replace humans on a 78% level. So our conclusion with our research is that it is possible to automate this task, at least in the sense of giving an estimate of what the CPEs will be, so that DVM tools are enabled to alert software developers and security professionals if they are using vulnerable software. But this system could be improved. We can see that we need more data in some of our labels, and we have also encountered some data quality problems, so we would like some higher quality data, maybe from additional sources such as GitHub. We would also want to try a TF-IDF Lexical implementation, which we've seen similar work been done with decent performance. And we could also benefit from having a security specialized language model for the word level embeddings. Thank you for listening. I hope you enjoyed my presentation.